Okay, good afternoon. I'm Frank de Ruik from the University College of Ghent, and together with Volker, we will present some very interesting JMP tools for process improvement based on the purification case study. Right. Okay, sorry. Yeah, the case, so let's start with, of course, the case problem, the problem statement. So the problem was a poor capability, purity of a chemical product because of an unstable manufacturing process. So because of that, there was a need of an additional purification step before really the final purification. Second problem was there is still time-consuming offline purity measurement, chromatographic purity measurement. So we only get very low amount of data for process monitoring and modeling. Okay. So starting with showing some baseline figures illustrating the problem. So we took a sample of 20 hours, 2 reactors, 2 shifts, and you see here the distribution of the purity for both reactors, reactor 1 and reactor 2, and showing that the PPK of both reactors are quite low. The second reactor is very low, only PPK of 0.2, which is, of course, not good. So we have really a problem with a lot of variation of the purity within reactors and also a lot of variation between the reactors. Also very interesting to mention is that the distribution of the purity for both reactors are not normal. It's a bimodal distribution. So the PPK, you can do this in JMP, can be computed based on this bimodal distribution. Also, we created some a graph, SPC graph, 3-way control charts of, for both reactors, showing that okay, the reactor 1 quite stable, above specification, despite of the low PPK, but of course quite close to the lower specification limit, and a lot of instability was observed for the second reactor. Why we constructed 3-way control chart? Because I think, of course, maybe just to mention that we was a sample of 20 hours, where for each reactor we took 2 samples per hour. So you can also construct an X-bar R chart, but of course the spread of the range chart is not very well to represent the natural process variation. Is better that the natural process variation. So the control limits are computed based on the moving average of the average purity of the 2 measurements per hour. But here you can also see that, of course, in the range chart, even for reactor 2, there is a lot of spread even between the 2 purity samples within 1 hour. Okay, so it's quite an unstable situation. And of course, this was the subject of a lot of root cause analysis, and the most important process effects were revealed based on that. We come back on that, which will be used for further modeling. So we have 2 goals here. First of all, a very important one, improve the manufacturing process performance. We want to reach a PPK of purity of more than 1 and a lower specification limit of 90%. If you can reach that, that should make it possible to reduce the extra purification rework, which of course is a very huge cost and also very time-consuming. Besides that, of course, we will have to improve our measurement process, and that replacing that time-consuming chromatographic procedure by very quick online NER purity monitoring. So we can, if this is possible, we can reduce skip the offline purity measurement, of course, and also we will get more, we can augment, of course, the amount of data for process monitoring and modeling. Workflow, we will start by launching the DOE for purity process modeling. Yeah? And this DOE should make it possible to specify a process model, yeah? Allowing to specify process control range so the purity higher than 90% can be achieved. And also, besides of this, we will also, together with purity measurements, also the spectra and the spectra will be recorded. And also by using PLS, we will assess the possibility for modeling the purity versus the NER spectral data. Okay. So if this is positive, if this is positive, it will be possible. We'll show it. It will be possible, of course. Then we will further assessing the potential for more in-depth, more advanced purity modeling versus NER using regression analysis, and also particularly machine learning methods. Okay, starting with the DOE, the response variable, of course, is the purity. And we will try to maximize, and we want to reach a low. We'll try to get it above 90% lower specification limit, and also the response variables. We will also, besides of the response variable purity, by the chromatographic technique, we will also at the same time record the NER spectra of the different DOE versus the different DOE runs. Okay. As for the process effects, we will have based on these root cause analysis and process engineering, 4 important effects are important: the temperature of the reactor, reaction time, pressure, and the dosing flow rate of the reactant. Here are the ranges of all parameters. And there is, of course, a budget. We only have 4 days. We have maximum 24 runs. So we will have 6 runs a day. So based on this information, we will try to the DOE was an optimal DOE because we were expecting that all parameters have a significant effect. So we made an optimal DOE for 24 runs. Okay, and it will be randomized over in blocks of 4 days. So 6 blocks per day. So there will be 4 random blocks in this DOE. So you see that there's quite a good coverage of the experimental space, and also the color map you can see that collinearity can be neglected. So this looks promising. Okay, the first model we created was the mixed model, because we have those random effects, the random day effects. And I think model Volker now will take over and show how this is done in JMP. Okay.
Yeah, let us have a brief look at the analysis of this experiment. As Frank said, so this was an optimal design using the custom designer in JMP, and the special feature here, or not really special, but what you should be aware of is that we added a random blocking effect. Yeah, I just want to show you where this has been set up. So maybe you saw that we have fixed blocking effects under the factors of the experiments, but we are not interested to learn about every individual day. we just want to learn about the overall variation between days. So we only want to spend also just 1 degree of freedom for this single estimate. And that can be done by having a random blocking effect. And this is set up here. So we specify the number of runs per block. So this would be per day in our case. And with 24 total runs, we would cover the 4 days in this example. So now the experiment is done, that the purity has been measured. We also see the 4 factors, our process settings, and here we have the result from the mixed model. Mixed model, let me show you the launch of the fit model dialog. What has been configured was the personality, of course. So here it has been set to mixed model, keeping the default options. And as usual, we have the fixed effects down here. And we have the random block effect set up as a random effect. So running this analysis gets us to this model report. So we see that we have the R-squared, just the variation explained using our fixed effects alone is already 94%, and adding the random effect does not really improve this. So this is also confirmed by this output here, the random effects covariance parameter estimates. And that's the section, if you analyze a mixed model, that's the place where you can really understand the structure of the variation in your data. Yeah, so we have the 100%, and some of that variation is just unexplained error, our residual. And in this example, we see that we cannot assign any variation to this block effect. So this tells us there doesn't seem to be any day-by-day variation in this example. So it's just about the fixed effects we want to learn about. And here we see that we have 6 significant effects sorted by p-value in this place here. So we can go straight to the profiler. This is not a standard prediction profiler, but the conditional model profiler, which includes both the fixed effects and the random effects. We only have 1 random effect. And again, it's confirmed that this is really flat. So changing the days doesn't really affect our purity. Now we are starting at mid settings of our parameters, and we can do an optimization here by adding the optimization controls, and then we can maximize the desirability. Yeah, and this gets us to a solution which is a minimum time setting and the other 3 factors set to their maximum settings. So this does maximize our purity. So that's our goal in this analysis. With this, I want to give it back to Frank.
Okay, thank you, Volker, for your very nice explanation. So I will now share my screen again. Okay. I go to, okay. Yeah, I go to here. Okay. So now we will go to a second modeling technique where also validation is possible. You can ask yourself validation, there's such a small data set, only 24 samples, you cannot split in a training and validation, but this can be done using with GenRec, in German, GenRec, and we call this the SVEM, the self-validation assemble modeling technique. And maybe here is the schematic overview how it works. Maybe just a few words before we do the analysis. So what we do is ensemble modeling. We will create an ensemble modeling. That means an average model of different models which are being validated. It's as a matter of fact an iterative process, and each iteration. Sorry, I will make sure that I have my laser pointer on. We'll start with a weight split into a training and validation set. What is done is that you make a copy of the training data and the validation. You copy your training data and you have the same data for the validation. But what you do is then you assign weights to end training and to the validation set, weights based on a gamma distribution. And the high weights for training or low weights for validation and vice versa. This way, okay, then you will fine and tune the model on the weighted training sets. And then you will store this final model. So I have a beta 1. And we do this in JMP by default 200 times. So we'll get 200 different models, validated models. Okay. And finally, the final parameter estimated in this matrix here. And so we will aggregate all stored models, and then this will produce a stable assembling estimator, this one here. Why we do this? Why is the motivation for doing this? Well, maybe. So this weighted resampling creates a synthetic variation, and this generates robustness and stability even when there are no replicated runs. What is happening in production is maybe you have just took a sample of 20 hours. It's a one-shot sample, but of course in production, okay, when time changes, also the weight of the different effects can also change. So as a matter of fact, this is like a simulation of the different models over time. And it is proven that because of this procedure, this modeling technique, this performs very well on unseen data. And any average many weighted models reduces sensitivity in the noise, outliers, and unstable factor combinations. And diverse resampled models also prevent the single model bias like we had from the mixed model, the single model bias. So, and that reducing overfitting. So, but of course you have many models, and with all their own root mean square error. And we will see model, I think Volk will show it now, how it works in JMP, that of course the prediction interval, the confidence interval is much wider compared to the modeling based on just one training example. So Volk, can you now show us how it works, this modeling in JMP?
Yes, I can do. So in this second demonstration, we will look at the self-validating ensemble model analysis Frank just motivated and introduced. And here is the starting point. So this uses fit model, and you choose the generic personality, which needs JMP Pro or the student edition. And the setup is that in this example, the Weibull distribution has been chosen for the response, and then the estimation method is set to SVEM forward selection, which does all the SVEM magic behind the scenes. You can just change the default number of models built using bootstrapping and all the techniques involved. But that's the default. And clicking go gets you to the model report. So as Frank said, it's a special analysis. So here we don't see any p-values on our parameter estimates. Instead, for SWAM analysis, we see a percentage of non-zero. So for all these 200 models, we check how many times an effect came up as an active effect. And the more that happened, the higher their, in quotes, significance should be. So going down, here we see the prediction profiler, and you also see the broader confidence bands Frank mentioned, and we have no stochastic error variation added to our process settings. They are all fixed right now, but what's already switched on is a response error, and that's random by model. It means that it follows the Weibull distribution of our response. And simulation simulates 10,000 data using Monte Carlo simulation, but using the fixed settings here and just starting at the midpoints of our settings of our factors. So instead of maximizing the desirability to look for the spot in this factor space where we have the maximum purity, we shrink the factor space. So we shrink the ranges of our factors using the design space profiler. So the subspace, the so-called design space, should cover as many as in-spec data points as possible. Yeah, how does this work? It also simulates thousands of data points uniformly distributed over the whole factor space. Yeah, we also see a scatter plot matrix of our factors down here. And the factor ranges have already been shrunk and optimized. And that means we already went down from all our data points. So these are all our data points uniformly distributed, but we are already down from these 100% to 5%. And that's not the sweet spot. It's the sweet space, so to say, the design space, which has many green data points. And green means the response, the single response in our case, is in spec. Yeah, and this happened for 99.9% of all simulated data points. Yeah, just to show you how can we change this, how does this happen? Yeah, so if I lower the lower limit of the temperature range, we get more data in. Look at this here. We get a higher volume portion and more data in, but more and more red. And that's what we don't want. So I go back to see just green if possible. Yeah, so I go back to 240 and take this as the design space. And now we can populate the design space back to our profiler, the prediction profiler. And that can be done on the design space profiler menu. So first thing, I send the midpoints of these ranges back to the profiler. So now the midpoints have been adjusted to be in the mid of these ranges down here. And I send the ranges themselves. So this is done by sending the limits to the profiler, and this sets the distribution of our factors, the random distribution following a normal distribution in this case. It's not uniformly distributed anymore. So this is now normally distributed, which can also be changed in many ways, but normally distributed. And now here we can do a simulation, and we see that the defect rate really dropped from over 60% to lower than 10%. And we can even take a further step, so we don't have to accept a random variation on all the factors. So just that depends on the system experience and system engineers. They have to tell us. And if they tell us, okay, we can really fix the time, so there's no need to have this time distribution here. So we can just say, okay, time is not random anymore. It can be fixed. And we can even set it to a better setting, maybe 11, which seems to be promising. Yeah, and then simulating again, so really drops the defect rate significantly another time, one more time. Okay, back to Frank.
Okay, thank you, Volker. This was very clear for you, presenting this SFAM method. So I'll share my screen again. Okay. Okay, and maybe I think we end up here. Just a minute. Okay. Yeah, another one. And that's everything what Volker told us. Here you can also make some graphs from the menu of in the generic menu. So we ended here. Yeah, there's the one. So we ended about the reject rate of 3%, which to my opinion is quite realistic. Volker didn't show you, but if you this is based, of course, on the random error by the model. When you would just add no noise, you would receive a 0 reject rate, and when you would add just some simple random noise apart from the model error, also it would be 0%. So this really is a big random model error because of the different models you will see here is the reason why we have still a reject rate of 3%. But to my opinion, this is more realistic in reality because I like this SFAM method because the just one single training model is every time you use this is too much optimistic. So because of time changes, also your model changes and your factor weight changes. So this SFAM model validation, we believe there's the best simulation of the real process evolution. So okay, we have then do some more homework. Of course, we still are with this quite high process model error. Here you can see the distribution because of random of the simulation study, which is the same, just shown on the generic screen. So, but now the goal is, of course, to how to achieve this PPK of 1, and then achieving a reject rate of only 0.15%. So we then, we have to start the PDCA cycle, quality circle, to and put some more effort to go there. And the most important goal is improve this process model. Of course, this cannot be done by our slow analysis procedure of a chromatic procedure, but it takes about 15 minutes. So we need to generate much more purity data, and we believe that this can be achieved by NES spectroscopy, of course, but then we need to model, of course, the purity as a function of the spectral variation. So how to do this? There's our input factors now will be the wave numbers. They are more than 1,700 wave numbers. We cannot, of course, model this. So what we need to do first, we will do a data reduction per principal component analysis and a functional principal component analysis. I come back on that. So we can model the purity as a function of those principal components and functional principal components. As I said, we together with the purity data in our design experiment, our experimental design, we also monitored the spectra, the NR spectra, and we do a PLS study. That means modeling the purity as a function of the principal components. We can see that two principal components are enough to explain more than 86% of the purity variation. So that's very good. And if we evaluate this model, you can also see where the weight of the different wavelengths in the principal components. So the spectral areas which are important. Quite some overlap, but see some spectral areas are different. But that is an important graph for the further spectral calibration we will also do in the future. So if we model purity as a function of the PLS model, what we can see is we already get to quite nice R-squared value of 85%. So that means that there is a proven relationship between purity data by chromatographic analysis and NER data. Only the thing is that we are at a low purity area, we have some false positives here because the prediction is below spec, and meanwhile the real figures are within spec. So here we still have quite some variation. So this low amount of data by what this experimental design are surely not enough to generate a predictive model. Why is that? Because if we make here a scatter plot of the scores 1 and 2, the principal component, the scores 1 and 2 of the principal components 1 and 2, sorry, we see that we are still quite some wide gaps. So we need, of course, to fill up those gaps to make a reliable modeling possible. So we need much more spectra. So what we did is, what we'll do is, because of the potential of modeling, we will first try to build also PLS models, generic models, so and also machine learning models by support factor machines to using the principal component or the functional principal component scores. How we will do this? We will add the 40 extra production NER spectra what we have have from our original sample, our production sample. We also took the spectra. We will add them to the DOE spectra, and then we will perform a principal component analysis and also a functional principal component analysis, and then we will partition we will use the principal component scores, not because the company I gave consultancy to was still had the normal JMP, so they didn't have the functional principal components, which is only present in a JMP Pro. So we use this, and we will of course partition this in 50 spectra for training and validation set for modeling. And also, we will also generate a whole bag of 14 spectra for testing the model. Of course, now the question is, what spectra we will use for making this model? What are now the best spectra? Well, we'll select these spectra based on a cover rate design experiment, which will give us the best coverage for the experimental space for making the model, the training and the validation model. And using this spectra, of course, we will generate validation set, 75% training and 25% of validation. So here are the results for the principal component analysis, the RE spectra plus the production spectra. And here are the results for the functional principal components analysis. The functional principal components, what is that? Well, the functional principal components gives us are representing the strongest variation of shapes. And the S spectra are very broad spectra, and very small shifts of the shape can also already give some chemical information. So those functional principal components, to my opinion, or to our opinion, is very interesting to model the shape variation of different spectra. And the models we will use for functional principal components will be wavelet models. You see the results. You see three principal components and three functional principal components explain 95% of over here the principal components, of course, of the total variance. And here the three functional principal components explain 95% of the shape variance. If you make again scatter plot of the principal components and functional principal components, what we see is that, of course, there's already a very big improvement of the coverage of the experimental space, but however, we still see some white spots, particularly for the test data, which are black. The black are the test, the holdbacks, the 14 spectra holdback sample are very centered in the middle of the of the spaces. So for the test spectra, we don't have a very well coverage. But okay, we have to live with that. We cannot, of course, specify the control ranges. We just have to have our spectra which are on the shelf. But here there's the coverage design, okay, told us which spectra give the best coverage for modeling our purity. So interesting also is that to check whether there is potential for modeling the purity. So when you collect distribution of purity together with the principal components and the functional principal components, you will see that the distributions for high and low purity are different. So there is you see it here, particularly with the functional principal component. The high purity corresponds with a high scores on the second functional principal components. It's even more clear than for the principal components. But that looks interesting. Maybe there is potential for modeling. Yeah, of course, I'm not going to show all the results of the different models. What we did, you can collect we did here in a model comparison menu the results of all the prediction models, the PLS model, generic for the principal components and functional principal components, the support vector machines both, and also for the neural network on principal components. What we can see is that's interesting that by shifting from PLS is the lowest performance or lowest square, and also the highest root mean square error. When we go to machine learning, we see a significant drop of the root mean square error. That's the one from generic, and here it goes down to about 1.5. Also, that's indicating that really we need to include higher order effects in our model, either very, very strong curvature, strong non-linearity to get good models. It can be shown very good when we plot the purity versus the result of the predicted results of our models. Here is the PLS. For the PLS, of course, it's just a simple linear model. You can see there's quite a strong lack of fit, very strong lack of fit. So the linear model is not good enough to generate a prediction model. It's already battled with the GenRAC on principal components and functional principal components. It's already better. And particularly for the machine learning models, the support vector machine and the neural nets, giving us R squares more than 90%. That's already very promising. What we can see is that here we have still a lack of data, spectral data, but for purity between 85 and 95%. Here we see a very strong gap, which corresponds with the gap we observed also in the scatter plot of our principal components. So we need, of course, more spectra to fill up these gaps, and I'm sure when we were able to do so, the models will be very much improved. Here you can see the results of the prediction formulas versus the scores, the principal component scores and the functional principal component scores. Here you see it for the PLS model, it's linear. Here for the GenRAC, it's a simple quadratic model. For the principal components and for the functional principal components, when going to the machine learning, you see much more curvature. Let's see it here. And when you go to a neural network, you have to be careful here with neural nets for overfitting. You can see that the curvature can get very, very strong. Yeah, where you, of course, you will have can have a risk for overfitting. But you need okay, those high nonlinear effects, to my opinion, it's proven to achieve good models. So as for the future, as to conclude, so that's a very good news that purity NER modeling is possible. That's very clearly proven. Best performance is achieved by the functional principal components, according to chemical information that looks logical, because shape deformations give quite good chemical information. But of course, we need to get more purity data and the NER to collect more data to improve the model performance, particularly between the 85 and 95% purity range. What we will do as an action plan, we will further study more in detail the impact of impurities, because impurities are known. So we can also create a model with impurity effects. We can create an experimental design, so to study very much more in detail the impact of the impurity on the NER spectra. So, and that will also very help us much in the spectral calibration and also determination of the interesting spectral areas for further modeling. So if we will, after collecting a lot of more data, more spectra, when we will achieve an acceptable predictive purity NER model, we will compute then the control ranges of those principal components and functional principal components, and then of course assess this models using offline NER purity control. And then we will of course collect predict purities and also compare them with the offline chromatographic measurements. When this is okay, when we have a good validated predictive model, when this offline method is validated, we will then go to online NER spectroscopy. And with online, of course, we will get a lot of data. We will have big data because every 2 seconds we have a spectra. And we will have to be able to predict, of course, many purity data. But the goal is then establish a model between the functional principal components or principal components and the process effects. So we will establish a functional principal component causal machine learning model. And if this is realized, then we have a possibility to automate the process. Then we can do advanced process control. Okay, that's challenging goals further to achieve. Thank you for your attention. And okay.